good? Yep. All right. Your guys' learning targets today are to differentiate between ionic and covalent bonding or compounds. You guys can compare and contrast them. You guys can also identify whether a molecule is ionic or covalent. Okay? Then you guys should be able to tell me, yesterday we talked about why molecules form. You guys should tell me the difference between how and why ionic form, how and why covalent form. Okay? And then finally we will talk about diatomic molecules, and you guys would be able to tell me what the diatomic molecules are. Okay? All right. So on page 22, you guys have pasted in that handout. What we're going to talk about is what a covalent molecule is, how do we identify it, some properties of covalent molecules, and then give you guys some examples, and then we'll talk about the diatomic molecules because they are covalent. Wake up, sunshine. Okay? And then on the next page, we'll talk about ionic, how are ionic different. Okay? So covalent compound is going to always form between two or more nonmetals. So if you guys were to look through all the symbols in a formula, and they are all nonmetals, that is a covalent compound or a covalent molecule. Buck, where do we find nonmetals at on our periodic table? No.
To the right.
To the right, to the right. Don't use that as, that's not how the song goes. They're going to be to the right of the staircase, or that bold line. Okay, so anything on the right, like boron, carbon, nitrogen, oxygen, fluorine, all those are nonmetals. Okay, you really have to force your noble gases to bond because they already have their 8. So that was the whole premise of why we form molecules to begin with, is so they can get 8 in their valence shell. All right, what else we need to know is that covalent bonds hold these two nonmetals together. Okay, and how they do that is they share their electrons. This is one of the big ones. So if I asked you guys to tell me what a covalent molecule is, you would tell me it has 2 or more nonmetals and that it shares its electrons. So if we look at our electron configuration, okay, valence electron is anything in our outer energy level. So in the instance of our first energy level, how many total electrons do we need to fill that level? Garrett? Just 2, okay? So we just go, the energy level is the number in front, 1s2. So if we've filled that, that one's happy. Okay, so an example here would be hydrogen. Okay, hydrogen just has 1 valence electron. Okay? It only needs 1 more to be happy. It's kind of an exception to the octet rule. We don't have a total of 8 to fill our first energy level like our second one, so it's happy with 2. So we have 2 hydrogen atoms. Each of them have 1 valence electron. Okay, one hydrogen atom is like, I have 1, I need 1 to be happy. The other hydrogen atom is like, I have 1, I need 1 to be happy too. So what they do is they come together and say, yo, you want to share these valence electrons we have? If we add up our 2 valence that are unpaired, we can share them, have 2, and be happy. Okay? Huh? It's like a little happy family. So you guys can kind of think of it as they hold hands. So it's a really strong bond because they're holding hands. They're sharing the love. They're sharing their electrons. Okay? All right, so some covalent properties that we see. Obviously, we already know it's all nonmetals. They do not conduct electricity. So in the lab tomorrow, what you guys will be doing is you will have several different substances, and you guys will take this little piece of equipment over here. It has a light bulb. We'll plug it in, so electricity will be supplied to it, but it won't be conducting electricity because this is what we call an open circuit. There's absolutely, why is it not following me now? Hello? Is it recording? All right, no big deal. All right, so we have this little setup here. These two prongs are an open circuit, meaning that there's nothing connecting these two prongs to conduct circuits through. So you guys will take different substances and you'll hold the liquid into those two prongs. And if it has the ability to conduct electricity, these two will then be connected by the fluid, and it will light up the light bulb. And then you guys can kind of tell how strong it is. So some might, even a covalent one might weakly light it up. But for the most part, your ionic ones will light it right up. So covalent don't conduct electricity that well. And we'll explain a little bit more why that is when we talk about ionic. They are not soluble in water. What does soluble mean? So it's the ability to dissolve. Good. Okay. So if we throw covalent ones, one of your guys' biggest you guys will see is like oils. Okay. Most oils and gasolines and stuff are covalent. So you throw them in water, they're not going to mix very well. Okay, sometimes they separate, sometimes you can just kind of see them swirling around on top, depending on what it is. Okay, versus something like salt, which is ionic, we throw it in there, it's going to dissolve right away. Really, really strong bonds, like playing red rubber when you guys hold hands. Okay, think of those little covalent, non-metal guys holding hands, and it's going to be really hard to bust through them. Okay, with that being said, that's probably one of the reasons they're not that soluble in water. But if we heat them up, okay, then we can break some of those bonds, use a little bit more energy and break some of those stronger bonds to get them to dissolve. So like sugar you throw it in water, kind of dissolves, but not that great. But you throw it on water or on a burner and you boil it, then that sugar is going to dissolve. So you really need to add some energy to it to get it to break those strong bonds and get it to dissolve. Has a low melting point. So if it is not already melted, generally, it's pretty easy to melt it. So one of the things you guys are going to do in the lab tomorrow is you guys will start a Bunsen burner. You guys will make kind of a little cup out of tin foil, and you guys will hold the cup over the flame. If it melts within a couple seconds, then it's probably covalent. Okay? And last but not least, it can either be a solid, a liquid, or a gas at room temperature. Does anybody know what room temperature is in degrees Celsius? It's about 20. Good, Garrett. It's about 20 degrees Celsius. Depends on whose classroom you're in. If you're in mine, it's probably more like 23. Okay? If you're in Mr. McKelkey, it's like two above zero. Was it? All right. Some examples. These are some common ones you guys will see, but by no means are you limited to these. There's a lot of covalent compounds. Examples. We have water. Water can act as either both, because it's sneaky like that, but based on how they share their electrons, it acts mainly as a covalent. Carbon dioxide, carbon monoxide, nitrogen dioxide. Ozone is O3. Sulfur dioxide. NH3 is ammonia. H2 and N2. And there's, like I said, a lot more after that, so etc. Okay, NH3 ammonia. Have you guys ever heard of ammonia before?
Yeah. Oh, that's good.
Wherever you hear of ammonia at? Oh, smell salts? You also have like that weird smell of a Windex is a lot of ammonia, and then the same kind of components in a lot of animal urine. You get a lot of ammonia content. It's one of the easiest to note, like identify as cat pee. So you can really smell the ammonia in cat pee, etc.
Is the SO big O or little O?
Big S, big O, sorry. I pick up my marker, but it still detects it on the board, so it smears it across. That's going to be my excuse for crappy handwriting. Maybe if I hang this around. Was it? Oh.
That could be very true.
I really only care that I guess, I don't know. Lies. Now it's not going to show the board. Cool. Oh, is it tipping back? Technology. Is it good? Can you see it just fine, Grace? Okay. The last little thing we're adding on this page is what we call diatomic molecules. So these are something that I expect you guys to know, but I give you guys some tools to help you out. Okay, so a diatomic molecule, the definition is that it's a molecule. Molecule being, in this case, more than one atom. Okay, it's a molecule, or let's see, scratch that. It's an atom that cannot exist alone in nature, or an element that cannot exist alone in nature. That's the best way to put it. So kind of like a little buddy system. If you guys go on field trips and you have bus buddies. Bus buddy. Okay, these are our diatomic molecules. We've got N2 is nitrogen. H2 is hydrogen. F2 is fluorine, not fluorine. Hey, just make sure you spell it right. You guys have a periodic table in front of you at all times. Never. O2 is oxygen. I2 is iodine. Cl2 is chlorine. And last but not least, we have bromine, Br2. So those are all of our diatomic molecules. Meaning, like, if we're looking at oxygen, we will never see one oxygen atom floating around in nature by itself, ever. Okay? It will find another oxygen atom to bind with, or to make a covalent bond, and then it will share those electrons. They're way more stable that way. You guys, like I said, will never see one of any of these diatomics floating by themselves. Why are they molecules? More than one atom. Okay? They're not more than one element, but they are more than one atom. Okay? We'll never see one single atom of these by themselves. So when we talk about reactions in a couple units and we talk about combustion, combustion is basically burning a fuel. But what do we need to burn something? Always. Oxygen, right? You guys take away the oxygen, you guys take away the fire. Okay? So when we talk about combustion and burning a fuel with the presence of oxygen, when you guys write that in a reaction, you guys will use O2, not O. Okay, you will never write a single O by itself without some other element with it or another oxygen with it. Okay? So if we're talking about, oh, this reacts with fluorine, it's not just an F, it's an F2. Okay? So these are our diatomics. So here's how you guys can remember these. I'm going to give you two tools. The first tool is going to be never have fear of
Invisible.
ice cold ice cold Barks, if you guys have ever had Barks root beer.
Oh, I was going to say beverages. Or beverages, that's better. I'll never have fear underdog.
That's not it, no. So never, N is nitrogen, have, H is hydrogen, fear, fluorine, of, oxygen, ice, iodine, C, or the C in cold is chlorine, and then Bargs root beer, the BR, is bromine.
Oh, that's
Okay?
right.
So never have fear of ice cold Bargs root beer. That is one tool to help you guys remember those. Get familiar with them because it's important that you recognize them and say, oh, hey, I know in this reaction or in this sentence, this word problem that Ms. Crawford gave me, that iodine is a diatomic molecule. So when I'm writing the formula for that, it's I2. Okay? These are the only ones that follow that. The other tool that I'm going to give you guys is what I call your cheat sheet. Do not lose this. Write your name on it. It is important.
We're done writing on that page.
Yes, we are done writing on that page. One, two, keep those past these. Yeah, ice cold Barks root beer. If you guys have ever had Barks root beer. Huh? Well, if someone can learn how to count up front, that would be great. Also, you guys need to get out a highlighter. We're going to be highlighting something on that. Alright, so if you guys notice the very first bullet point on that says your diatomic elements. Okay? Never have fear of ice cold Bargs root beer. It lists them, it gives the formula, and then it gives you guys that first tool to remember that never have fear of ice cold Bargs root beer. Okay? It's on there, very first bullet. So this is something that you guys will use on every test if you need it. Okay, not all the tests we will need it. Like next unit when we do moles, we won't need these. Okay? But this unit we'll use the crap out of them, and then when we do reactions after moles, we're going to use this a lot as well. Okay? So that first bullet has your diatomics on it. The other part of this that's important is this data table right here. Okay? So what you guys have in here is what we call polyatomic ions. This is the only thing that I make you guys memorize in here. Okay? I do not make you guys memorize the periodic table and stuff like that. Okay? We even write stuff on the periodic table so you don't have to memorize it. This is important though, and you guys can ask anyone who's taken chemistry that actually cared about the grade before. This will help you identify these. So when you guys are doing naming and writing formulas of your compounds, this will be easier for you and you will do a better job. Okay? So out of all this list, this by no means is all the polyatomic ions that exist in the world. These are probably the most common that you guys will see in here. But we have some that are even more so common in terms of what we use in class, and those are the ones I expect you to memorize. So with your highlighter, let's highlight some of these. In the -1 charge category, find C2H3O2 minus. It's the second one down. That's acetate. Highlight that one. You guys need to know the acetate ion. Skip a couple down. Find NO2 minus. You guys will highlight the next three, or the next five, excuse me. So NO2 minus, nitrite. NO3 minus is probably one of the most common we use always, is nitrate. Cyanide, CN minus. Hydroxide, OH minus. And permanganate, MnO4 minus. What? Huh? So again, nitrite, nitrate, cyanide, hydroxide, and permanganate. Skip a couple more, find chlorate, ClO3 minus, and highlight chlorate, ATE. ATE. Aren't you guys glad I have those long A's to really emphasize? ATE? You guys don't get it confused with ITE? Alright, go down to the ones that have a -2 charge. Okay, we'll skip the first two. Sulfite, SO3 2 minus. Sulfate, SO4 2 minus. Carbonate, CO3 2 minus. And chromate, CrO4 2 minus. Those four. So sulfite through chromate you need to know. You guys will do both. I'll explain that to you in a second. We won't have this quiz for another like 2 or 3 weeks, I think. But in case you guys want to get a jump start, since you already have this, you can study if you want. Go down to the charge of -3. You only need to know phosphate out of that one. PO4, 3-. We use that one a lot as well. And the very last one, charge of +1, ammonium. Different than ammonia. Okay, this is ammonium because it has gained an extra proton in charge. Okay? All right. So you guys can kind of start studying these now if you want. How the quiz would look for this is sometimes I'd give you like nitrate, and you guys would tell me NO3 2-. So I'd give you the name, you guys tell me the formula and the charge. Or I give you the formula and the charge, CrO4-, and you guys would say, oh, that's chromate. Those kinds of things. Okay? So it can go both ways. I also am going to send you guys a Quizlet flashcards link if you guys want to practice flashcards on your own. It has all of these on there, so it's not just the ones that are highlighted. Okay? And then that link is also on my main chem page if you guys want to study those as well. Okay? All right, let's talk about ionic compounds then. So we'll talk more about what these are later. We haven't really gotten into that yet. We will, don't worry. Okay. Ionic compounds are going to form between, I've been doing that all day, a metal and a non-metal. The metal will always be listed first. So if you guys look at a formula and the very first element listed is not a metal, with the exception of hydrogen, we'll talk about that here in a second. If the very first element listed is either hydrogen or a metal, it's going to be ionic. I'm so sleepy. All right, so let's talk about this. When you guys look at the word ionic molecule, what do you see? Ion. We all know what ions are now. So Jocelyn, what is an ion? I know. You're even on video. Don't mess up. What have we changed when we've made an ion? You're not even going to try to hide that he gave you the answer. Cool, take your head off. All the way off. So ions are any time that we have either added or taken away electrons. Okay, so Tristan, if we lose an electron, what charge does that give us for an ion? Positive. Buck, if we gain an electron, what charge does that give us? Negative. Now we have a positive charge and a negative charge. What do we know about a positive charge and a negative charge? They are going to attract each other. So this is the whole essence of an ionic molecule. Okay? We form ions first. Then, if they're opposite charges, they're going to attract to each other like a magnet. Okay? That's going to be an ionic bond. So let's talk about this. Why do we use a metal and a non-metal then? No, because with covalent, we don't form ions. Right, metals are always going to form a positive and a non-metal is always going to form a negative. Good. Okay, so that's why we have it between a metal and a non-metal. A metal will lose its valence electrons and create a positive ion. Okay, a non-metal will always gain an electron to form a negative ion. Now we have a positive and a negative. They're going to attract to each other. Okay, non-metals for covalent, the reason, obviously, if we had two ions with that, they would repel each other, right? We wouldn't be able to put two non-metal negative anions together. Okay, they would kick each other away from each other. With that being said, we don't even make ions to begin with covalent. Okay, we only make ions for ionic. Okay, it's in the name, that should help you. We never make ions first with covalent. Okay, we only do that with our ionic. So how this works is instead of sharing their electrons, they are first going to give and take their electrons. This is the important part of that. Give and take electrons. to form ions. The metal will form a positive ion. And the nonmetal will form a negative ion. That's an I. Something like it. Since opposites attract, the cation or an anion will form a bond, an ionic bond. Taken, not shared. There's actually a cat meme, one of those cat scientist memes, that says that. My name is Bond. Ionic bond, taken, not shared. See what I did there?
Yeah.
Who comes up with this material? Like, I want their job. I also want to be someone who just does Excel graphs all day. They get internet cred. I got internet cred.
John Internet.
All right, again, so you guys form an ion first. We have a positive ion because we have a metal, and we have a negative ion because it's a nonmetal. They attract to each other, and that forms our ionic bonds. Okay, so if we take a look at sodium chloride we know is an ionic compound because the very first element in there is a metal. It's on the left of that stair step. Sodium has one valence electron. Okay, table salt is, like I said, sodium chloride. We look at chlorine. Chlorine has 7 valence electrons. So what's going to happen is sodium's like, dude, I got to get rid of my electron anyway because I am not stable right now. I either need to gain 7 or lose 1. It's easier for me to just get rid of this one. And chlorine's over here like, yoo-hoo, yoo-hoo, I have 7, I need 1. So sodium gives chlorine its other extra valence electron there. And now chlorine's got its 8. Okay? So now sodium gave up its 1, so it has a +1 charge. Chlorine gained 1 to get 8, so now it has a -1 charge, and that positive and the negative charge are going to be attracted to each other. There's a little bit more to it when we'll talk about, because like someone said, I don't know if anyone said it in this class, but in my other classes they said that, well, they're going to want to form neutral molecules, they're going to cancel each other out. Yes, every molecule that we make is going to want to be neutral, so eventually when we have different charges, they don't agree with each other, we're going to have to change the number of them. We'll talk about that when we talk about writing ionic compounds. Okay, so let's talk about some properties of ionic compounds. Obviously, the first thing is that we know that they're a metal and a nonmetal. Your metal's listed first. Your metal's listed first. If hydrogen is listed first, this compound is ionic. Okay, so for instance, one of our examples that we look at is hydrochloric acid, HCl. Since the H is listed first, it's going to act like a metal. But if we look at something like methane gas, CH4, the H is listed last, it's going to be a nonmetal. Okay, so that's going to be the difference of having an ionic substance versus covalent. HCl, hydrochloric acid, is ionic. CH4, methane gas, with that H listed last, is going to be 2 nonmetals, so covalent. Okay, so pay attention to that first thing. It's either a metal or it's hydrogen. It's going to be ionic. All right, how do you guys think this compares in terms of strength of the bond? Why would you say weak?
They're not sharing the electrons, so they're not
Right. Basically, yeah, the covalent are sharing. They're really strong because they want to stay stable and have their 8. They're literally holding hands. Okay? Versus sodium and chlorine, they've given it up to form 8. So on their own, they're fine. Okay? They only are brought together by an attraction, so it's kind of like pulling 2 magnets apart. Very doable. Okay? Versus trying to break someone's hand in Red Rover. Because they're, like I said, they're stable on their own as ions as well. Or you could just dislocate their elbow. What? That's got to feel good. Too soon, Garrett? All right, so they're going to be a really strong bond. Or really a weaker bond, I guess. Okay, we're going to see because of their ionic charges, stuff like that. When you guys see the word electricity, what does that remind you of? That's chemistry. Electron. So anytime you guys have some kind of electrical current, it's all because of electrons that are moving around. Okay, in this case, we got electrons moving back and forth between sodium and chlorine. It allows us to be able to conduct electricity. So ionic compounds are great conductors of electricity. So even in your body, you guys have electrical currents flowing all around you because you guys have all these ions and ionic compounds in your body. So anytime your brain is sending a signal down to your nerves, that's all electricity. Okay? Anytime your heart beats on its own, that's electricity. Anytime you move a muscle, that's all based on electricity because of these movements of electrons. So when you guys see someone die in the movies and they're like, we're losing them, clear, what are they doing to them? Why? How are they? They're giving them electricity, trying to restart their heart because you have a natural electrical impulse in your heart that is stopped. By shocking yourself with electricity, you can restart that. If you get electrocuted, it's like the opposite. Your heart wasn't working to begin with. You hit electricity with it, it's going to disrupt it. Your heart will stop. So it's kind of the opposite. If you guys have a working heart, you get electrocuted, it stops your electrical current in your heart. If you guys have a stopped heart that has no electrical current going, you give it electrical current. Okay, so kind of cool. But yeah, a lot of electricity in your body. Whoa, what happened? Okay, soluble in water. What's that? You're doing it wrong. But why do they say clear? What is the whole purpose of it being like clear? So no one's touching it because your guys' hearts are all working just fine. But if you guys get that shock of electricity through you, it's going to stop your heart. So that's why they're like, clear, don't touch the dude because you're going to get electrocuted. So soluble in water. You guys throw salt in water, it's going to dissolve pretty quick versus some covalent compounds. It's going to have a high melting point. So we will hold some ionic compounds over our Bunsen burners tomorrow, and you guys will see that it really would take you guys holding that over there a long time, too long for the aluminum foil that you guys will be using to get them to melt. Okay? The aluminum would probably melt first. And then last but not least, they're going to be usually a crystalline structure at room temperature. Oops. Oh, man. Which is a solid. A crystal is a solid. So most, not all, but most ionic compounds, as long as we haven't thrown them in water in their natural state, most ionic compounds are solid. What do I mean by crystalline? Does anybody know? Oh, shoot, classes, I'm sorry. Yeah, if we were to, it has a special arrangement of its ions, so it would form a specific shape. And like if you guys heard a piece of salt has a cube shape, that is the arrangement salt will always take. So if you take a hammer and you crush a bunch of salt, it's going to always be in like a little cube shape. Okay, others have like hexagonal shapes or like 2 pyramids stuck at a base, things like that. Your examples really quick. I don't know why that won't go away. Examples are going to be NaCl is table salt. MgBr is, get these down real quick before you go. FeO is rust. If you guys were to take a piece of rusty metal, scrape the rust off, the formula would be FeO. Fe2O3. HCl is hydrochloric acid.
Can you please report to Eddie's office? Vicente Acosta.
Ooh, H2SO4 and MgO are some examples.
Is that an MY?
That's MgO.
HC1. What is that?
HCl.
Is that a 1 under
No. There's a comma.
SO what?
FeO, comma.
H2SO.
We got NaCl, MgBr2, FeO, Fe2O3, HCl, H2SO4, and MgO.